Yeah, what I have to do with the online thing, do I have to do anything?
That's a nice easy question, that one.
Oh, okay, so we just, yeah, we're just giving them the audio. That's fine. I'm not going out for a minute. Probably less than a year. I like it, but let's still get. Yeah. 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 And then you can read them out. Yeah. Yeah, that's not okay, but maybe so, okay, I'm clearly playing the online audience. Yeah, I can. Sure, and I'm off. It's possible. Thank you, yeah. I'm good. It's just sorting out the online. I feel like everyone's oh yeah, yeah. Oh, wow. Scoop. Yeah, it's good to know. It's good to know. By the way, you get like to that week, right? Right. Oh well, it's nothing. Okay, looks like a nice punctual start. So thanks everyone for finding your way in. Yeah, so just a couple of upcoming events to tell you about. The website's a little not up to date on this, so you kind of might be hearing it here first. October's event, so as many of you will know, we typically hold events the last Wednesday of the month, and October is no exception on that. We have an event the last Wednesday in October. I forget what the actual date is, but really importantly to know that's going to be held at the iStructD rather than this place. So so if you find yourself here on that evening, you're probably not going to be able to make it across town for that. So better to get the right venue to start, I guess. That's being given by Atif Rashid, talking about a new seismic isolation system based on pre-Inca technology. So it sounds pretty interesting. I think Atif might be the recipient of the SecEd fund. I'm seeing some nodding heads. And important to note that that will be preceded by the Young Members AGM, so the Young Members Subcommittee AGM. So I forget the start times exactly, but do check the website. And if you're interested in attending the AGM, get there early for that. We just discussed just now in our committee meeting that we will have a kind of networking event after that with some drinks and nibbles. So hopefully that'll be a good event to turn out for, not just for the technical content and the AGM, but also for the sort of networking opportunities. A little bit off the normal calendar, early November, November the 5th. If you're not otherwise busy on that evening, we have a event co-badged with the Offshore Engineering Society. And that's being given by Gopal Madabushi. I forget the exact title, but it's something to do with seismic design of offshore wind foundations. And that's an online-only event, as I say, co-badged with the Offshore Engineering Society on the 5th of November. And then back at the ICE, back in our normal last Wednesday slot, November the 26th, we haven't got a full title, but it'll be something along the lines of developments in seismic hazard models and ground motion models for the UK, being given by Ilaria Mosca of the BGS. The exact content of that needs to be drilled down on based on how much they get done, I think, in time for the meeting. So that kind of takes us through the rest of the year in terms of our calendar. We do have a number of other events kind of heavily penciled in for early next year, but kind of watch this space or watch the website for details of those as they get cemented. But I think now we can turn to tonight's event. So Miguel Martinez-Paneda from Arup presenting tonight. He's a principal structural engineer at Arup in London and also a researcher at Imperial College. He's a chartered engineer and did his master's in architecture in Madrid, and then a master's in structural and earthquake engineering at Imperial College. He's actually, for a relatively young fella, he's picked up a number of awards already in his career, including the 2020 iStructE Young Structural Professional Award. And of interest to this audience, and kind of part of the reason we invited him to give the talk, was that he won the Best Paper Award at the 2023 SECED conference. And hot off the presses, I think perhaps breaking news, tomorrow he'll be awarded the Royal Academy of Engineering Young Engineers Award. We timed it absolutely perfectly, not quite deliberately, but so it's great to have recipient of all these prizes speaking to us tonight. So Miguel's going to be talking about structural damping in tall buildings, evolution, challenges, and a new integrated approach. As usual, plenty of time for Q&A at the end, hopefully. And over to Miguel. Thank you.
Thank you, Marcel. Okay. Thank you very much, Damian, for those kind words, and thank you everyone for joining here on this afternoon. It's very nice to see so many people here. I was slightly skeptical to see what will happen, but it's good to see also some familiar faces and others. So first of all, Damian has already mentioned the topic of the talk. I will start, first of all, with acknowledgements of the people thanks to who were able to deliver this work, like Professor Ahmed El-Ghazuli from Imperial College, Kevin Gonder from Aeronautics Imperial, Will Algar from Arup, Dave Burkett, our model maker, Damian from Arup, Damian here as well, Melissa Burton, and then Paul Howard, Ricardo Huerta, Will McCardo, Susanna, Leslie Clark, and Mark from Imperial Civils and Aeronautics. It's quite a big effort that I will try to explain. Let's skip the introduction. So first of all, I'm gonna talk more or less gonna be around 50 minutes. I'll try to give a kind of quite wide background, I hope, sort of building from the fundamentals going up, going from tall building design, so what is damping in tall buildings, to end up finishing at the integrated damping system, which is the system that we have developed and that we're proposing. I've worked through my career in a series of tall buildings. You can see a few of them. The one I'm more proud of is the last one, BDO Unibank headquarters, where Pedro, who's sitting on the audience, also helped me work on it. So that's also it's now under construction and going build, and then let's see what happens. And then if you go straight into the topic of damping in tall buildings, a tall building is as simple as a single cantilever. It's a cantilever where you have like some loads, which are the horizontal windows and the horizontal windows applied to it. And in a similar manner to any normal cantilever, what we want to do to have an efficient cantilever is make it as deep as possible and concentrate the masses at the corner. And that's the same that we see in a tall building where we have a vertical cantilever that has a horizontal load applied to it, call it wind or seismic, and that is the basic behavior. There's nothing more complex than that. What we want to do is we say, same as we're doing in an ice standard beam, we want to place the mass at the ends and have them as far away as possible. That's going to increase our stiffness and our efficiency. It's not the same having a chunky beam, but a relatively deep and slender one. We generally will say we place a structural mass, we refer generally to concrete, because concrete behaves really well in compression and other stiffness to the building. So it's a really good material for tall buildings. And this is the example that I'm using is the Caja Madrid Tower in Madrid, where the two cores are very efficient because they're connected and the structural mass is really far away from the corners. We have a weak direction, hence why the mass is concentrated at both ends in the other direction as well. But it's as simple as a tall cantilever. And the same you can see for the common flank tower. The purpose is, okay, we want to make our beam as deep as possible, and therefore we place a structural mass on the ends. Sometimes you do have other constraints, which say, that means the beauty of tall buildings, that there's so many things interacting, and you cannot really over-design. You have to be very efficient. And so there are many interactions in construction, services, views, fabrication. So there are many varieties, a central core, which sometimes can be beneficial, maker frames. It all depends on your specific site, your program, and what you're trying to achieve. Then it is okay, like it's like any other building. You have gravity loads and lateral loads. The key thing about gravity loads is that for a tall building, the loads accumulate, and they make a huge difference. So you do want to be as efficient as you can to actually know what you're designing for. I quite like always this graph to illustrate, okay, how much does 5 kPa mean, and whether it's actually realistic to design for that. If you design every floor for that, you're going to end up paying the price at the bottom. That's why we generally go for, say, composite floors and slide solutions. And that is especially because loads matter. This is the column at the ground floor of the China Sun Tower, which is a 60 square meter column, which is quite a large apartment. If that's the question, like, you can actually live within that column, and it's a question of whether you want to have actually elements that size in your building, or if you can make them more efficient because it adds a lot of value. And as well, it's also not so much reducing them as well. How you're smart about it. This is for 425 Park Avenue, a building that I really like. It's like, how do you transfer the gravity loads to potentially transfer some to the core? So rather than working in tension, it's in the compression, so it's not crack, it's more efficient. And how you create a better office space or incorporate those transfers as outriggers and as features in the space. There are many considerations that go there. But then if we go to lateral. So lateral, we have wind and seismic. Starting for wind. Tall buildings are generally investigated using a wind tunnel test. So the Eurocode tells you the moment you're above 200 meters, you need to use a wind tunnel, or certain slenderness ratios, there are a series of parameters, but it's the standard approach for any tall building. You generally design them for, you want to check in the wind tunnel the along wind and the crosswind direction, because it's very important in tall buildings, as you can see on the graph from below, with the crosswind excitation, which is a phenomenon that happens as wind goes through a bluff body. So in a building, it creates some vortex at the end, which is the effect you see there, that excite the building out of plane. So even if wind is blowing in this direction, what we're seeing is that the building is going to be moving out of plane, top and bottom. And that's usually what governs the design of tall buildings. Moreover, in the wind tunnel, you also check them for strength and service. So you check on one side the ultimate limit state at 700-year wind, and so to prevent the tower from collapsing, the maximum storm, but also the service condition, which, okay, what is the 25-year, the 50-year wind for drift and top displacement. And as well, what ends up governing tall buildings, which is accelerations. Tall buildings tend to be governed by accelerations, which is usually with a 1-year return period, also evaluated on the wind tunnel, which is, okay, as users, we don't really perceive movement or displacement, but we are really good perceiving acceleration, translational, and rotational. That depends on what activity we're doing. If we're laying in bed, we are more sensitive. If we're walking less, if there's music playing, there's a series of parameters that makes us especially susceptible if a tall building is moving or not. And then if you go to seismic, we just design it as any other building, following capacity design principles. we identify a series of elements that are going to behave as fuse and going to dissipate energy. For example, one of the most common things are, we use concrete cores, we have coupling beams joining the cores, and the coupling beams break yielding tension and cracking compression. It's like yielding, behaving a flexural manner to dissipate energy in that cracking and yielding of the reinforcement. And therefore, we are able to reduce the seismic loads in the building and avoid over-designing to remain elastic under a seismic event, as we will do with any other building. The difference for tall buildings is more that right now it's very common for any tall building to do performance-based seismic design. When you're doing, okay, many codes as well prevent you from doing certain tall buildings or a relatively efficient version of them using code procedures, so you have those performance-based seismic design. And what you do there, you assess the behavior of the building under the service level earthquake, which is the one that happens every 43 years, and in order to ensure that it remains fully operational, and under the maximum considered earthquake, what you want to, the maximum considered risk targeted maximum considered earthquake is the one that happens every 2,500 years, and you want to prevent collapse. For other types of buildings, say airports, nuclear plants, you might have other objectives. That's what performance-based design is about, but allows you to go slightly beyond code, but only checking the serviceability, and that ultimately limits the state. And then is that wind and seismic interaction, especially it's a very good point where we have in this tower video that was in the Philippines. So we have very high typhoon-prone region and very high seismic. So how those two come together? What we generally design the building is to remain elastic under wind and only start dissipating energy and experiencing damage after wind loads have been exceeded or the service level earthquake. In this case, for example, as you can see, the wind loads are the solid lines and the service level earthquake are the dashed lines. Wind loads were almost double the seismic load. So wind was the one governing the design. If we were to check the maximum considered earthquake, the base shear is way larger than wind, but that's when we say, okay, there we can accept damage in the material, we can use expected material properties, we don't need to use nominal for all elements, there are more things that we can do. But then, as a quick summary of this, like what we do always find is accelerations tend to govern. Or if not, it's top building displacement or interstory drift, accelerations tend to be the more common thing. And in order to say, okay, in order to kind of make sure that wind-induced accelerations are within comfort limits, as the graph that I showed you before, so you get the wind tunnel test, you get your acceleration in your building, you go to that graph and you identify where you are, whether it's for a residential or for an office floor, you take each line. If you're above, it means that your building shakes too much, you need to bring them down. In order to do that, you can either stiffen the building, add more structures, increase the structural sizes, add more elements, which that was what was done 50 years ago, but it has been proven longly that it's not really inefficient, besides a costly and expensive manner. Then what you can also do is that you can shorten the buildings. Like sometimes you can make it a bit shorter and you get less wind loads. Or you do aerodynamic modifications, such as cutting the corners or like twisting it. However, for example, cutting the corners is also you're losing space, or shortening, which is the same purpose what you're doing in the building. So to what extent it pays off is kind of a question that needs to be looked. However, one of the common things right now that is one of the most widely accepted is just to provide supplementary damping. And that's most widely accepted. And then when I was, okay, what is damping in tall buildings? So damping is the capacity of a system to dissipate energy under, so like, for example, if we get a ruler and we pull it, fixing at the base, it's gonna start vibrating, but vibration is gonna little by little start to reduce. The rate in which it's reduced, the speed at which it reduced, is gonna be the level of damping. So it has very low damping, it's gonna vibrate for half an hour. If not, it's gonna go really fast. Buildings typically have, well, before I go into that, and that's very important because when saying, okay, both wind and seismic are both dynamic loads. So they're not going to apply to the building as a static, even though sometimes we might check them like that. Therefore, damping has a really big impact on how the building behaves dynamically, and especially under resonance. So then say typical buildings have a 5% level of damping, but tall buildings, as we increase the height of the building, the amount of intrinsic damping that the building has reduces to around, maybe say a 300-meter building has 1% damping. And as well, it's worth noting as well, that depends on the type of material, you get one value to another, so concrete a bit more, steel a bit more. But even though, if we think, okay, what is generating damping in a building? Is cracking within partitions, movement within steel connections, heat dissipated. And then it sometimes assumes that okay, the more amplitude you get, the vibration, the more damping you're going to generate. But that's not necessarily true, because the moment all the cracks in the partition have opened, the seals for the facade are broke, you might actually have experienced a reduction in damping. So that's one of the points as well. Like you have to be relatively careful if you assume a relatively large value of damping for your design, but then in reality, there's going to be hysteretic damping. But if you assume that account for that separately, you might be on the risk side. And that is especially if it looks at this is the plot from our turning moment from a wind tunnel test from a building that our colleagues in New York did. And when you see like a building say has 1% damping, you see the blue line at the top. And the moment you increase from 1 to 2% or to 5, there's a massive reduction in wind loads at the base. So even a slightly overcounting for it might drastically increase your demands in your building. And that also shows you the large benefit that you have in a tall building if you can increase the level of damping from that 1 to 2 or 5% to literally halving the demands. Interesting as well, you also see how from 1 to 5 is a huge decrease, but from 5 to 10 is only a marginal gain. And that's for, even for low-rise building, you do want to have like large levels of damping. For high-rise with 6, 7, 5%, you're already mitigating most of the dynamic response. You don't really need to aim for 30% damping. And then as well is the, I guess most of you have seen the collapse of the tower in Bangkok. If not, it's worth watching for awareness, obviously. And then towers don't tend to collapse under seismic events. Damping will reduce the uncertainty, but also the key benefit of having a damping system is non-structural damage. We have seen in the East Japan earthquake, and many other recent ones, how many buildings experience large accelerations that lead to significant non-structural damage, which is way more expensive than structural damage, can lead to significant downtime, that for commercial purpose, or even any kind of life critical, of course, but can have a really big impact in the community and after seismic events. And then, okay, so based on what I've seen all of these, like what are the benefits of damping? So they can help control wind-induced accelerations, which are the reason why mostly they are implemented in tall buildings, as I'll show you later on. It improves dynamic response, therefore it can improve seismic response, and it can reduce wind-induced dynamic effects. If we have a redundant system, we can reduce the wind loads because the building is not going to break as violently as before. It's going to be smoother, therefore less demands. We get savings, as we saw from the plot. In terms of we go to types of damping systems, we have passive, active, or semi-active hybrid. That is depending on the level of interaction with excitation. Japan has some active systems and relatively well spread, but the most common ones are passive systems. That's because they're more reliable. They don't rely on any kind of energy or active input, which you might or may not have during a seismic event. If you have generators, but those are the most common ones. In a similar manner, they can also be categorized as distributed or mass dampers, if there are many elements on the height of the building or several, or a mass damper, which is just using a mass. And then if you look at those two categories separately, I'll try to kind of like give a small explanation. Okay, what are the examples now on buildings? What can you see? And it's like, there is no answer of what is the best damping system. It's more a relationship. It depends on every single case, which one is more applicable, because each one have their pros and cons. Therefore, I think it's also worth seeing them. The first application that was done of a damper was in the Twin Towers in New York, was 1969, where they used elastomeric dampers that work dissipate energy by shearing, and they were connected at the bottom core of the truss to the facade. They were able to generate 2.5 to 3% damping with 10,000 elastomeric dampers. And they become really popular to mitigate wind-induced vibration. And that's, for example, that's on the Columbia Seaford Center. You can see these very large braces that are everywhere. They were able to generate up to 6.4% damping. It's a massive amount of damping. However, the use of the bad thing of elastomeric dampers, especially back in the time, they dissipate energy via shearing, and they dissipate energy within the damper via heat. However, they have temperature-dependent properties. So under large events or seismic, the material will experience significant damage, and the use reduce once fluid viscous damper became available. Material have improved throughout the years, and for example, there's a new use that new application that I think is quite interesting, is that viscoelastic coupling beams, where rather than having those concrete coupling beams that I was showing before, we have a series of steel plates with elastomeric material in between, and dissipate energy between the shearing as the tower is swaying in one direction to another. This one have been implemented in several buildings, and they tend to have a quite robust behavior even under large wind events. As I was mentioning before, so yes, elastomeric dampers become less used with fluid viscous dampers. When fluid viscous damper that came from the military and aeronautical applications came into civil engineering maybe 40 years ago. Those of you that are in London might recognize the Millennium Bridge. There are several types of damper, very interesting to go there and spend some time looking at all these different systems, but they have fluid viscous damper. They generate damping by the differential motion of both ends and by passing fluid from one chamber to another, typically silicone. Interesting, they cannot resist any static load. This is a shock absorber of a car without the spring. So if you push them, they're gonna yield. They can offer resistance to dynamic loads, but it's important to know that you cannot really account for them to just resist a static load. They're a velocity-dependent device. And why is that important? Because the force is tied to velocity, so the maximum force happens at the maximum velocity. That is very relevant for retrofit applications. So when you have an existing frame, and the building sways, when it's at the point of maximum displacement, the force on the frame are the largest, but the velocity is zero. As the building comes back, velocity is zero, and velocity displacement are zero, forces are zero on the frame, but the velocity is the maximum at the equilibrium point. Therefore, the forces in the fluid viscous damper, if you use them diagonal, for example, are offset with the structural forces. So you might not need to strengthen the frame, and you can still improve seismic response. And they can dissipate very large levels of energy. They were implemented in the Torre Mayor in Mexico, one of the first cases for seismic applications, where they implemented 98 fluid viscous damper up to 20 meters long, and they proved successful in resisting seismic events. Or more recent applications that, for example, include motion amplification devices to increase the level of damping that you get, which is one of the challenges with elastomeric dampers. So with distributed dampers, and is the fact that they rely on the differential motion between both ends or plates or dampers cells, but in reality, tall buildings don't really experience very large interstory drifts. They behave more in a flexural manner, as you know that 1.5 meter core that we might thick core wall that we might find at the bottom is not going to experience much movement from 1 floor to 4 meters higher. So it's for tall buildings, you generally need to have either mega braces, as we were showing before for Torre Mayor, motion amplification devices, or other systems that can increase the differential displacement between both ends. And that was the same for the scalpel here in London, where what we did here, we have these mega braces around the facade, concentrating the movement from the top to that setback level to provide the fluid viscous damper at those points and concentrating all that differential displacement on the height. In this case, they were done for wind applications. And the interesting thing as well is that the dampers cost less than 200,000 pounds, but enable a saving of 2.5 million, that will be the TMD, or up to saving 2,500 tons of steel and the proportionate part of carbon emissions, which is a very large kind of number, as you can see, and it can bring very large savings. Another building that I really liked was like 181 Fremont Street, also like really, really impressive how everything is done. In this case, it was done for wind and seismic, and they are designed to work in parallel with backing restraint braces, but also with the same concept of having mega braces connecting 2 points of the corners of the building and concentrating those differential displacements on those elements. Other application as well, where we say, okay, we want to concentrate large movements between or large forces, and we can place the damper there. It's like rather than having a conventional rigid outrigger, what you can do is you break, because the outrigger connects the core to the mega columns to stiffen them up. Well, rather than have a solid connection, you can replace by a damp connection. And the good thing about this one is a good campus, as you get really a lot of damping. And the reason why it sometimes is beneficial just to have a rigid outrigger, but for example, these towers were done in Manila, where you have very high winds and very high seismic. So in a way, if you were to, so these are residential towers, where are more sensitive to accelerations. If you were to connect it rigidly, you are increasing the wind response. However, you're drastically decreasing the seismic response. You're making your building more rigid. You're increasing seismic loads. However, by placing a damper, you are both mitigating wind-induced accelerations, but also improving the wind-induced seismic response even farther than you would be by just connecting rigidly. You can see a picture of the construction here. And interestingly, so these fluid viscous dampers have a very large damper coefficient. So they had these kind of vertical fins to dissipate energy, and they have that valve which they were designed with a nonlinear damper exponent. So if there is a very large seismic event, to avoid inducing excessive force in the outrigger, the moment you exceed the windows, the valve kind of opens, and you can reduce the effect that the damper outrigger has, softening the building considerably. Another system that is like different than the previous one is backing restraint braces that will fit within the hysteretic devices, the one that experience damage, mostly for seismic applications, experience damage by hysteretic behavior, yielding basically. Backing restraint braces are formed of a steel core with a concrete encasement. So the steel core yields in tension and compression, and so without backing thanks to the concrete encasement, and therefore they're able to provide a very robust energy dissipation mechanism under cyclic behavior as compared to normal braces that would yield in tension and buckling compression. We did this for a project that was involved as well for China Merchants Bank. It's a really good paper by Xiaonian, Yuqi, and Minsheng on describing about them, where we have up to 31 meganewtons backing restraint braces were working in parallel for the outriggers to engage the core with the mega column, and as well for the BDO Unibank headquarters in the Philippines, where we have 90-meter long backing restraint braces. And the good thing about backing restraint braces is that you can use them to increase wind stiffness against wind demands, but whenever you exceed that wind demand, they can start yielding and then dissipate energy in a seismic event, which is what you see that's an image from Perform 3D, where I was finding how all the braces were yielding, which is good. Once the seismic demand was exceeded, the braces were yielding, were dissipating energy. And when looking at the time history, what we see as well is that the backing restraint braces were responsible for 65% of the energy dissipation. This is using a nonlinear response time history analysis that allows you to track, get the buildings subjected to an earthquake, how it's going to respond, and you see the energy that's dissipating the different components, or how much it moves, you can track all of that. And we can verify that the dampers perform a really good function. The last one in terms of distributed dampers, it will be like this, for example, a really good source of friction dampers, which are now picking up quite a bit. And that's for the Habeno Arukas Tower in Osaka. It's a 300-meter tower, the tallest in Japan. And this one, for example, has all kinds of dampers. It has friction dampers, hysterectic, oil dampers, NTMD, and just dissipate energy by friction at the connections. The one you see on the left, that's by tectonus, is a different one that, for example, includes self-centering capabilities, which is one of the things with backline restraint braces of friction. You have inelastic behavior, but then that means extension of the base or rotation of this case of the friction devices, which can lead to permanent displacement and offsets in the building, which you need to correct later on. And before we go to mass damping systems, one sec. So then, okay, that is the thing about distributed damping systems. They're really good because they're frequency independent. They can work really well for seismic response. They're redundant systems, so you can account for them to not just reduce acceleration, but also improve seismic response and wind. But they're relatively slightly inefficient, let's say, for tall buildings because of that very small interstory drift and the fact that you need to connect them really far apart to concentrate the movements of several portions. Mass damping systems are probably the most common ones in tall buildings, and the most common one of all of them is a Chima's damper. What a Chima's damper is based on the vibration absorber, and it's just kind of, if we have a main mass which represents the building, so every building has a natural frequency, the frequency which vibrates, we add a mass to the top, and we tune that mass with a spring and a damper to match the frequency of the building, so it vibrates out of phase with the building and therefore creates an equal and opposite force as the building moves. They generally have a mass ratio of 0.5 to 1% and can generate from 1 to 4% damping. And potentially the most well-known example is the Taipei 101, or at least that's the one I always use as an example when talking to someone outside of the industry. It's a 700-ton TMD, where it's hanging at the top, as you can see there. It can generate up to 3% additional damping during when the vents is locked during seismic because it can create damage. And that's one of the bad things, well, before. Other example could be the Shanghai Tower, where you have 1,000 tons TMD hanging at the top. And that's, as you can see here, I mean, the bad thing of TMD is that they take a very large space at the top of the tower, where it's more valuable. You can imagine the value that has all the area that is taken, especially at such premium location. You need to strengthen the structure to support the weight of the additional mass. They are specifically frequency tuned to the frequency of the building, so they're not very suitable to resist seismic events. They are not a redundant system, therefore you cannot really account, so you can only account for the damping they generate to reduce wind-induced accelerations. You cannot reduce wind demands or seismic, as I was mentioning. And no, but besides all that, so they have a series of disadvantages that prevent them from making the most of the damping they can generate. So that 2.3% damping, if you could use it to reduce wind demands, that kind of overturning plot that I showed you from the wind tunnel, that would make a massive difference. But still, they're very popular use because they're really good to control wind-induced accelerations. They're way better than increasing the size. And then other application could be the tuned liquid damper or tuned liquid coolant damper, where you use a water tank at the top of a building with some baffles or screens and dissipate energy as water crosses those screens with the friction that happens there, viscosity. And then you tune, so you need to tune the size of that tank to match the frequency of the building as the water moves from one place to another. It needs to match the frequency of the building. And that was what we did as well for China Merchants Bank, where there were like 2 water tanks either side that were able to achieve from 0.6 to 1% damping depending on this wind scenario. No. And then, okay, there was kind of a bit of introduction of dampers. One of the key themes, so like dampers are generally represented by the same 2 degree of freedom simplification that I showed you before. We have the main structures is the first degree of freedom, the first mass, and the top mass is the mass of the damper. And that's usually accepted and works, gives really good predictions. The parameter that influences the most the behavior of TMS dampers or their effectiveness is the mass. The heavier we can make the TMS damper, the more efficient it's going to be. You can see the plot here. As we increase the mass ratio between the damper mass and the main mass, the level of damping that you can generate increases drastically. However, we are certainly limited in the amount of mass we can move. Say for the Shanghai Tower is 1,000 tons, but that's quite heavy, let's say. You cannot really go very high percentage. And that's like, there are many researchers that are trying to investigate, okay, what if we use roof garden TMD, where you have a heavy garden at the top, which is what many people dream of, and you can tune that to match the frequency of the building. Or what if we suspend every single slab and have it suspended and tune that suspension to like match the frequency of the building? You need to double the structure, like few implications. Another one is, okay, what if we have intermediate mass isolation system? Like what if we break the building at mid-height and we put the top part in elastomeric like bearings, rather than having a base isolation, we have it mid-height and have the top part behaving as a damper. That is also picking up in Japan right now. And then like our Tokyo has just finished one of the 2 buildings of a plot, the Hanuba, like the Shibaura Tower, where we have like a 50-meter more or less portion that is moved as a partial mass isolation. But the key thing that is very useful and works really well for low rise and mid rise. But once you get to a high rise, you're actually creating a software interface. So what they do in that case, for example, they incorporate an active TMS damper at the top to counteract that. So it has beneficial for damping, so for seismic, but it can be detrimental for wind-induced vibrations. It depends on every case. And then that's what kind of takes me to the integrated damping system, which is more or less building of everything that we have seen so far. And it's okay, what can we, so we're looking at it and like, okay, looking at everything that we have seen, it's okay, we know that the mass is the parameter that influences the most the performance of TMS dampers and how much they can behave, damping they can generate. But what we also know is that the more mass for a given target damping value, so if you want to generate 2% damping, the more you increase the mass, the smaller the differential displacement you have between the main mass and the damper mass. Moreover, as we increase the mass, we also increase the robustness of the system. It's less sensitive to tuning, and it can cover a wider frequency range. So it doesn't need to be perfectly tuned to the building to get that optimum behavior, or at least a really good behavior. But I think taking these 3 concepts together, another thing that we can acknowledge is that all buildings move. And it's fine. So, I mean, the public might not always know it, but as designers, we know that the building is going to move. there's nothing really we can do about it. It's going to move. So this building is moving where we stand right now, and not just because the Earth is moving, it might be millimeters, but what we're saying before, we don't really perceive those movements. What we perceive is the change in acceleration. So provided that we can control those accelerations, the fact that the building moves doesn't really matter. So what? And then is the next question, okay, can we use the building movement for our own benefit? We're used to always the same things as static, but what if we, okay, let's accept it, it's gonna move. The question, can we, now that we accept it, can we enable that moving and use it for our own benefit? And that's when we came up with the idea of the integrated damping system, which is what we're saying, okay, what if we we are able to mobilize a very large portion of the building? So one thing that the buildings have is mass. Buildings are extremely, extremely heavy. So if we can mobilize that mass and just have a very small differential displacement with regards to the lateral system, we're able to generate very large levels of damping. So we get that mass, a usable portion of the building, several floors, and we connect it with the springs in parallel with fluid viscous dampers, springs to resist the static wind load. We want to control how much that mass moves. We don't want that mass to be perfectly tuned as a two mass damper because it will move too much, but we don't need it to be perfectly tuned. We want just a few millimeters. That's going to give us already a very large reduction in response. And that's all we need. We don't need to aim for 50% damping. And then we have a fluid viscous damper that dissipates energy and also helps us ensure that the wind-induced accelerations in that portion are within comfort limits, so that mass moves very, very slowly. So we really have no idea. And then, yes, we can generate damping through minimum differential displacements thanks to the large movable mass. And then we look into it using a 300-meter tall building, where we have a central core, a steel central core, where on the top third of the building, we have the floor plate moving differentially from the core. We have a joint, so the lateral stability system is just a central core, very simple. And then we have perimeter columns, which are just gravity only. And we have a joint between the core and the floor plate, where gravity loads are transferred via corbel, and we have a series of springs in parallel with fluid viscous damper at 45 degrees to resist the torsional mode, and to control the differential displacement that we can see between the core and the floor. You can see another view here. You see the central core runs continuous, the leaves and everything, and you have this small gap between the floor and the core to allow the floor to move differently with partitions, so you don't really see any visual cues or anything. We investigated this numerically, first of all. We kind of get simplified model where we have every floor represented as a lump of mass, and for the floor and the core, and then we have the spring in parallel with the fluid viscous damper connecting them. And we're able to see for a maximum differential displacement under the Eurocode static wind load, even though we know wind is never static, out of 150 mil as reference, that we will come back to later on, we're able to generate 6% damping for that 50-year wind load, which is a very large number if you recall what we saw from before from the previous graphs. Checking as well under seismic, numerically all this, well, we found comparing that a rigid system exactly the same but rigid to the integrated damping system with a damp response, we're able to generate a reduced top displacement by around 40% under different earthquakes. It depends on how the earthquake is. It changes a little bit if it's more harmonic, if it's pulse-like, but you always see a reduction in response. And the same you can see in all the different performance index. Say top displacement we mentioned 37%. If you see drift, which is the first graph, comparing the rigid with the damp system, we see a reduction in 36%, acceleration 72% at the top, but overall reduction reduced. I think we're basically isolating those floors from the seismic event. They have no idea what's happening. But even the core sees very large reductions. And then the acceleration, the differential displacement for 7 records that we tested with scale 2.25 G, so a moderate seismic event, we have an average of 58 millimeter differential displacement. So not that much really for a seismic event. And then is when we say, okay, we have done all of this work and we managed to verify that the system could actually work numerically as a concept. And that's when we got we got funding from the Institute of Civil Engineers, and then together between Imperial and Arup, we're able to secure funding to do wind tunnel testing and dynamic seismic tests. What we wanted to do was investigate this experimentally, so do a model which explicitly incorporated the system. It is not post-processing, especially because the interaction with wind is a bit complicated, and it's not that easy to predict. CFD is not as reliable as our elastic wind tunnel testing. But those of you that might be familiar with wind tunnel testing, you'll know that our elastic models are very oddly done because they're very, very complex. On this case, it's quite ambitious, so it was quite an undertaking. But we're aiming to do a scale model of a 1 to 300 of that same building that I've just showed you. In order to do that, we're able to propose a new system that is currently being about to be published, a new kind of approach to designing aeroelastic models. We're combining using GSA Grasshopper. We created a parametric aeroelastic model, so a digital twin of the physical model. We were able to iterate to match the dynamic properties of the building to the model. So what is just as a bit of explanation before, an aeroelastic model, so for wind tunnel testing, you generally do rigid models, either high frequency force balance or high frequency pressure integration, which are rigid model with pressure tabs or a balance at the bottom, where you get the wind demands from there. Or the most complex part is where you do an aeroelastic model, which is a model that replicates the dynamic behavior of the building. So it has to match and be a true replica of how the building is going to behave dynamically. And that's where you can actually assess how it's going to behave in a realistic manner. Here you can see a view of the building, of the model that we have, where we have a central core. And we divided the 65 floors in 6 blocks, where we have the 4 blocks as rigid, the 4 lower blocks as rigid, and the top 2 as movable. So we have a series of dampers, miniature damper and a spring connecting those 2 blocks at the top, which are 12 stories each, and they are allowed to move differentially from the core. We detailed them so you could also make them rigid if you want to, just to be able to enable that comparison. We provided the model with acceleration, accelerometers, and a base load cell to get both the demands at the base and the response throughout key levels throughout the height and in all directions. And so this testing was done at Imperial College, like wind tunnel testing, aeronautics, which is very, very good. And we did, as it was such a complex model, we needed to make sure that the model was a true replica of the behavior. Otherwise, it was pointless, or we would be checking something completely different. We had to do thorough testing as we're building through every different stage. And then you can see a view of the model here in the wind tunnel. That implied weighing every single equipment. And at the end, what we see, we got a really good match between the target properties and the building properties. So we have 7.5 was our target, 7.5 Hertz. That's accounting for the frequency scaling. And we got 7.58, which was a very good match for elastic models, especially accounting for the complexity. And here you can see a view of the model. I also quite like this view, so left it on purpose. And you can see kind of a zoom view of it, where you can see the miniature dampers here with the rigid bar, which right now we have it in place when we're testing for the rigid configurations. But if not, we'll just unscrew the skin, remove the rigid bar, and leave the damper with the spring. And you can see these are the 2 movable blocks. You see there's a gap between them, they're hanging, and they're provided with all the accelerometers and everything. And then a view from this is kind of a video where we have, so before I go into numbers, I think it's very useful to see the video where we're comparing the response under 180 kilometer wind of the rigid and a damp case. So the top will be the damp and the bottom the rigid. And I think the video is very graphic of the difference in response that we have. So that's damp, rigid, and this. And see vibrates quite a bit more. But there's no any differential displacement almost between the skin and the core. There's tiny displacements. And that's a view of the model. And then if we look at the time history, so there's like displacement with versus time, or acceleration, not displacement. What we see in dark blue is the rigid model. In other colors, so we tested this under 5 different configurations. There was like, so okay, what if we have a softer spring? What if we have a medium spring or a stiffer? Or what if we lock the 5th block and we only allow the top one to move? We wanted to exploit all possibilities. Actually, the top only worked really well. But you can see that all of them perform really well and well below the demands that you can see from the rigid case. It's a massive reduction in response. If we look at this, so we're checking maximum acceleration, RMS acceleration, along wind and across wind. What we can see is there's a massive reduction in accelerations. The blue, the same color code as before, blue, solid blue is the rigid, and the dashed lines are the different configurations, and all as for increasing wind speed, so up to 160 kilometers per hour. What we see is that accelerations drastically reduce in comparison between the rigid and the damper case. I was like, yeah, values. The same we can see with the spectral density, the energy, our spectral density, the energy in the system reduces drastically. You can see the blue line and how we manage to mitigate all those peaks. And also this one is completely removed. This is for two different speeds. We also observe that the test has a bit of amplitude dependency because there's friction, there's stiction in the damper, there's a series of parameters that don't make it as ideal as the kind of a numerical model in terms of just behavior, but it's still really good response. And then if you check a base here, we're able to see like the long wind demands were reduced by 37% and a cross wind by 46%. So that's, if you think of the amount of material that you can save just by that 30% reduction, if you can drastically reduce the amount of carbon and cost that is in your buildings. And then the torsion as well, which like many damping systems struggle a bit with torsion. We're able to, just having the damping 45 degrees, we're able to reduce torsional moments by up to 59%. So we're turning moment follow the same as the base shear. And if we look now at a 360 degree, so just rotating the table, the previous values were 0 degrees, so where wind is facing the tower. And as you could see, for example, yes, across wind, what I was mentioning before, the demands are larger than a long wind, is that a crosswind vibration is governing, which is what you saw as well on the video. It was vibrating more in this direction than vertically. It's that kind of vortex-induced vibration effect. And sorry, yes, as we look at 360 degrees, we see how, especially when you have vortex-induced vibration at 0, 90, or 180 in the crosswind direction, is where you get the maximum reduction, and the tower is vibrating dynamically. 45 degrees is not such a big peak, but a damp system is able to drastically reduce the demands on those peaks. Using the random decrement technique, we're able to get the damping from the time history, and we're able to see that the tower can generate up to 4.4 additional damping. A bit less than what we predicted with the computer, but the same. There's a physical model, it's not going to be 100% accurate. And you can see there's a bit of variability. This is the curve that we will see. And this is also a reflection of the amplitude dependency. We could not push the model more because we were afraid of breaking it. That was as well the point. Once you see the model at the base shaking quite a bit, we're okay, when should we press the button? Because at least we're not really experienced of what's going to be the turning point. It changes between every model. And we didn't want to, we did some seismic tests, as I'll show you before. We didn't want to break the model at that point, or at least until we did the seismic test. And then the other question that we had, that was one of the main questions, what we want to do with wind tunnel. How much does it move? Because we were using the kind of that static wind load from the Eurocode, but we know that that static wind load from the Eurocode is not realistic. It's just a static load, representative, extremely useful, but it's not realistic. Checking for the 50-year event, we're able to verify that all the configurations move less than 50 millimeter at the maximum acceleration displacement. So that's a really, really small displacement even for the 50-year event. That actually reassures the large reductions that we can get just by having a 50 millimeter gap. And the large event is going to move that, but you're not even going to notice it. And it's something that within MEP detailing is very easy to integrate. You can integrate it right now within conventional detailing. And then we go to seismic. And this will be the last portion of it. So it should be relatively close to finishing. Yes, seismic test. We did this at Imperial College in the structural laboratory as well. And then what we basically had, we had the same model attached to the base. We removed the load cell because we were afraid as well. We were afraid of breaking it. We're not really sure what. So the load cell could take, I think it was up to 30 Newton meter or something similar. Kevin would be able to correct me. But then we were afraid of putting these larger loads and could damage it. So we just have a rigid base and we have an actuator in one direction that was going to create the seismic load. You can see a view here of the damper, like the model, just the gap, the thermometers. And then before doing the seismic test, we did harmonic tests, which are very beneficial to see how the system behaves. So we did an harmonic test for it was equivalent to 3 hours till the tower reached steady state, and then get the peak response at different frequencies. And we're able to plot the graph on the left, where you can see for the rigid case, the peak is very, very high, and that small bump is the second mode, which is 7.7 hertz crosswind. But for all the damp case, the response was drastically reduced. We're also able to see the differential displacement between the core and the facade. The facade representing the office floor, where we have small masses to represent the office floor. And you see the rigid case, this peak is because it was moving so violently that even the flexibility of the system was increasing the level of this differential displacement. But you can see that all the damp case do show that small differential displacement. Forget about the magnitudes because it's just based on, it's just related to the, if you have a 3 meter top displacement, you can get 120 millimeter differential displacement, but it's like, when are you going to have a 3 meter? You might actually have way less. And then we say, okay, we look at the seismic response. We took 7 records of different shapes and colors to try to hit it with different things. And what we saw is another video where I think it's less graphical than the other one, but it's still good to see, a rigid case and a damp case under the same seismic event. Sorry, damp and rigid. And you can see how the rigid moves less, moves more. The view is not more graphical from the top, but it's still, you can see how the rigid case like shaking quite more violently, which more or less gives us like, we were expecting this already from the numerical analysis and the results from the wind antennas, but it's one of those things that it's good to verify. If we look at the wind at the time history, that's what we see as well, like the same color coding as before, blue the rigid case, the rest in dashed line, and we can see that a significant reduction in response. A bit less at the beginning, that's why it performs a bit worse for pulse excitation, but for harmonic it does work really, really well because it's able to resonate, even if it's not offset at all as a TMS damper. It's a detuned TMS damper, and we're doing that on purpose, so we're able to mobilize such a large amount of mass. But even so, we tested as well in the 3 amplitudes, as a low amplitude, which is equivalent to 0.25 G, 0.65 G, and 135 G. Hence why you see the different kind of average maximum displacements, how it increases. And we are also comparing with that digital twin. So we're replicating every single test that we have experimentally, numerically in the computer, because we had actually, besides the real building, we also have the physical model in the computer. So we're able to achieve this comparison with the digital twin, quite a good matching response. And the important thing, a drastic reduction in vibration amplitude when comparing the rigid to those damped cases. And the same questions that we had before. What is the differential displacement? For the average for the 7 records are 0.25 G, so moderate earthquake, we're able to be always below 30 millimeters. So it's quite a tiny displacement. It's not nothing for a seismic event of that magnitude. And that's the last one. Then that's a bit of conclusions. Okay. What I've been trying to do is, first of all, set a bit the scene of where we are, what are the benefits, or like what current issues that we have. But I mean, what we have shown is that we're proposing a novel damping system that we try to make the most of what we have. Rather than adding mass to a building, we need to kind of make the most of what we have, and we have lots of mass available. Like, can we not use it and just enable a differential displacement? So the system overcomes conventional TMD limitation and is applicable to tall buildings of all heights, as it does not rely on reducing tower overall flexibility. The other one I mentioned, for example, for distributed systems, rely on a certain flexibility within floors. So they have a certain high limit because you cannot make your tower more flexible for the dampers to engage. So they can only be applicable generally from up to 250 12 meters. After that, they become less efficient. And as well, with the numerical and experimental test, we're able to verify that we can generate large reductions in response with minimum differential displacements. And as well, which I think is a key one, as we're mobilizing several floors, we're able to create a redundant system that can greatly reduce wind and seismic response. And with that, if we go back to the previous graph, where we say, okay, for 1%, we're just at the top. If you can just 1% more, I would say if we go to the 5%, the amount of reduction that we can have, which is what we have seen from the wind tunnel test studies, it can make a huge difference in the design of tall buildings. And we can go taller, make our structures more efficient, use less carbon, and overall lead to also an increase in resilience of that reduction in accelerations. There's going to be less downtime after a seismic event, and overall a better performance. And with that, thank you very much for your time. Please let me know.
Thank you. Right, thanks very much, Miguel.
Stand
Really, yeah, stay up there, it's fine, or you can have a seat, either way, yep. Yeah, great talk. Thanks very much for that. We've got some good time for questions. Nothing come through online yet, but those watching online, feel free to also raise questions. But anyone in the room want to kick us off with any questions or comments for Miguel? Ian. Oh, sorry. Do we have any microphones? We do. Valentina's coming down to help. Thank you.
Does it work?
We give that to Valentina. Thank you.
Hello, Ian Smith from Atkins. Thanks, Miguel. Oh, that's fascinating. It seems so simple, but it's such a great idea. So thank you very much. I was interested, and this is an aside really, with such a cross-sectional shape in plan, you're very prone to vortex shedding, and obviously if the wind angle is on the diagonal rather than square. So did you do anything on that aspect of the building in terms of trying to control the wind and the vortex shedding and the reattachment and things like that?
So like that's what I was mentioning before. So you
Yeah.
can drastically reduce vortex shedding if you do transfers in the corners.
Exactly.
The bad thing about that is like you're losing area. Even I mean a small chamfer, even say 1/8 of the building can already make a big difference. On this case, we're just testing, okay, what if we go for the maximum area? Because we want to maximize profits. As a developer, you want to build a building, maximum profits, and just build a square, which like it is more prone to vortex-induced vibration. Yes. And we did test as well, so yeah, 45 degrees. And that's where you see vortex-induced vibration is not that critical, but it will reduce the response. Potentially, so yes, it's like one of the things, like when you, what I was mentioning before, either you can increase the lateral stiffness of the building, you can modify it, which sometimes even the rotation can help of the building. I think if there's a prevailing wind, that's what happened in Burj Khalifa, you might know as well, they rotated a little bit and they were able to drastically reduce the wind demands. And the same, like if you transfer the corner or that kind of dynamic response, that can also be very beneficial. I actually have some few slides on that because, for example, one case that I was mentioned recently in a talk is the Shanghai Tower. It's really an interesting building, and they do kind of incorporate a rotation that can divert the vortex setting, and it's really efficient. What is the bad thing about it? The Shanghai Tower has been almost empty for many years, or 80% empty, because in a way you have way less efficient floor plate. You have this, the floor plate is kind of triangular with rounded corners and rotates, but the actual user, so the envelope is triangular with rounded corners, but the central is only a circle. And that circle is far away from the facade. So you're getting a drastic reduction in demands because of that rotation and the facade tapering as well towards the height. But when you're in the floor plate, you're also far away from the glass, and you're also losing lots of area. Nonetheless, that's answers the question, corner modifications can also help reduce that kind of wind response. And it can be another mechanism. It depends on the application, but they can make a big difference as well.
Thank you very much.
Okay. Brilliant presentation, Miguel. I just had a question. What consideration do you take to decide where to split the masses of the building?
Yeah, so ideally you should do a cost-benefit analysis where you say, okay, every floor has a linear cost, but the most effective ones is at the top. The top ones is where you have a larger normalized mass ratio, therefore they're more efficient. We started testing 1/3 because it was okay, we thought that would be a good starting point, and then we see how the system performs. In reality, what we found from the wind tunnel and seismic test is that actually even just the top module, so 1/6 of the building, will be very beneficial. For a practical application, what will be a matter, okay, the first floor is extremely effective, the second floor a bit less, and then it gradually decreases. It's not a linear behavior, while cost is relatively linear. So it's kind of an interaction between both curves and say, okay, what is the most efficient? From the point of view that we don't need to target 10%, 15% damping. Maybe with 2% damping, 3% damping is enough. So you say, what if we have 10 floors moving or 5? What if we have, like, say, the MVP floors and a few more at the top, which are the movable ones, and that's enough? So it's a trade-off. So that's a good question from the point of view. Like one of the things we found from the test, that we don't really need both. Just the top was extremely efficient for that.
Yeah, maybe just a continuation of the sort of design questions. You may have discussed this already, but to what extent is this dependent on tuning frequency tuning, and to what extent is detuning in a nonlinear seismic event an issue?
Yes, it's not. So we are everything is we did investigate, for example, what if we have nonlinear springs that allow further displacement during a seismic event? It didn't really make a big difference. It's not the key things what we were showing before, the fact that as you increase the mass ratio, you increase the sensitivity to the tuning. And what we're doing is like, if we were to have the mass perfectly tuned like a TMS damper, we will generate a huge amount of damping. But what we're saying is like, if we were to do that, the mass might move 300 millimeter, and that's not really viable, or it will come at a large expenses, and or users might actually perceive it because of visual cues. So we're saying that's not what we want. Just with a few percent, like 5%, that's already enough. So we're purposely detuning the mass. The more, so like, yes, you're detuning it, but it still has a frequency. The closer it is to the frequency of the building, the more damping it's going to generate. So it's almost on a case-by-case basis how your detune mass, or rather, not detune mass, rather you set the spring stiffness to control your differential displacement. You don't care about tuning at all. If it happens to be relatively close, so it's going to dissipate energy over a very wide range. If it happens to be very close, it's going to be better. But even if it's far away from the main frequency of the building, going to still dissipate energy.
Okay.
And the system doesn't really experience damage, as in everything is designed to remain elastic. If the tower suggests in a seismic event, if imagine you have MC level, there's damaging other elements, and the period of the tower were to change, as we're able to cover a frequency range, if it will be tuned to optimum properties, we will see a reduction. As we're not, it doesn't really matter. We already detuned, so it's not going to change much.
Okay, thank you. Ian again.
No, that's good.
Unless there's anybody else. Right at the beginning, you mentioned about the way you can actually have active and passive systems. You went through a nice summary, which I thought was really helpful. The advantage of passive systems is they tend to fail safe because they're inherent in the building. With an active system, even though it's not that active, it's just very clever. If something starts to malfunction, have you studied the sort of vulnerability that then arises from that?
So there are usually yes, that's kind of one of the risks of active systems and why people tend to be a bit more worried of them. You have semi-active that kind of compare like have an active component, but then kind of if by any chance say electricity kind of stops, they just start behaving passively. There's examples of TMDs, for example, that I've seen. On this case, I'm not using it. So one application could be, okay, what if the damper exponent, because the damper exponent optimum for wind is different than the seismic. They're very similar. But what if you were to change the damper exponent according with the seismic excitation? You could get a better response. And then if anything fails, you just resort to the default one. It could be an option, but it's like, so yes, for active systems, you generally have a generator in the building and a generator dedicated to that system. But there is those hybrid semi-active elements that allow that flexibility in case anything happens. You can go to default, maybe not as effective, but at least not detrimental, or you lock it.
I just wondered if you maybe have pairs of systems, so you don't lose everything. You maybe lose, say, if a coral spring fractured, then you've still got another one.
Yes, it's very interesting. For example, the Shibara Tower, the one that I was mentioning in Japan, so like the Tokyo office did, or the one in Osaka, the Haruba's 300. Those ones have it's like incredible the amount of damping that they have, different systems, and it's really, really smart how everything works together. Or the Type A 101 that has the main damper, but that one during a seismic event they lock it, and they have as well other things, dampers in the spire and other things that behave different than a seismic event. So you do have to kind of account a bit for that redundancy, which is the reason why you say you cannot use GMS dampers for a seismic event because they might break or they might be under maintenance. There was a talk by RWI where they were saying, yeah, we went to the building, they were complaining, but then because of induced acceleration, we went to export the damper and they had it locked. So like, okay, yeah, if you have it locked, it's not going to work. But imagine if there were to be a wind event at that location when you were accounting for the damping. Hence, by distributed, for example, you can account for that reduction to improve response.
Great, thank you very much.
I've got a couple of questions online, but we'll take Swanan first.
Thanks, Miguel, for a nice presentation. You mentioned that like cleverly use the mass that is already available in the building. How significant is the advantage compared to the conventional addition of mass. Just a anecdotal example, I think you showed Millennium Bridge. Now it's a concern with all the dampers in place. There might be too much of a settlement now because in original design, all that added mass wasn't considered. So I think even in the buildings, that might be a significant addition.
I do think it's like the mass that is right now in the building, which as in how the mass variation in the building might affect the performance, as you're thinking, right?
Basically, how significant is the advantage with your system using the available mass, not adding additional?
Yeah, so I mean, it's kind of a question. So we, for example, for this case, we were using normal weight concrete on all the top slabs and lightweight concrete because it's also very common in tall buildings, but it has a bit more carbon than lightweight concrete. But we kept the slab the same throughout because it's more realistic. To what extent? So like you can add more mass, and like on the actually on this paper on the third one, we do show how much you increase the mass of the mass ratio. You do increase the performance, depending as well towards your optimum frequency tuning, but as well as to what extent, because if you increase mass, you're increasing damping, but you're also penalizing the columns, you're penalizing natural system, increasing seismic loads. So you kind of, it could help, and it would be a worth of, does it pay off? In a way, we were, okay, let's try to aim for what we think is the most efficient one. And then you could do a study, okay, what if we add 20 millimeters more of concrete or 10 millimeters more concrete per floor? That's going to be very beneficial. Or you put heavy users at the top. But then how is that? It's a matter of doing which one has less carbon and cost throughout, which one uses less material. But there is a benefit. If we were to increase mass, there is a benefit. Quantifying it will be on a case-by-case basis almost.
Okay, I'll take a couple of the questions online. So I'll bundle a couple from Nicholas Hucker together. So he says, fantastic idea. I assume he's talking about your ideas and not earlier in the presentation when you were talking about others. Let's see, I'm wondering that if the occupied floors are being used as the damping mass, how does the amplitude of motion of the floors compare to the motion of the building? I assume like the floors themselves that are being kind of isolated. And a follow-up question from Nicholas, would this approach require areas of the building where occupants move from the main building structure to the floor, essentially movement joints for them to step out of the lift corset onto a floor slab?
Yes. So the amplitude and the differential of movement involved. If we will be perfectly tuned, we will have an equal and opposite direction, so maximum amplitude. What in reality happens is that there's a small offset between them. So like the curve goes and then the floor follows slightly after. It's like and that small offset is what creates that damping effect. But there is a differential displacement where you need to cross through it. That's what we're saying. Ideally, we say it can be adopted. So we present a central core building, but I think one of the first papers we had as well with a mega frame building, where you have the lifts running continuously, and as you get out to the lift, you have a movement joint, which you can have conventional detailing because the displacement that we're talking is absolutely minimal, but you will be stepping into the other area, into the movable area, let's say, and that services usually will have to cross that. And we were doing kind of an exercise within Arup. Okay, what is the requirement for services to incorporate this? Is it really doable, or even for fine compartmentation? And even with conventional detailing, the one that you have right now in buildings, you can already accommodate that. Services are detailed for thermal expansion, MEP services, and contraction, so that allows that flexibility to move the differential displacements. The fire joint between compartmentation between floors, you have mineral rock as well between them, which is compressible. Hilti has some products that can do that. And as well, you can just have a conventional movement joint detail, which is for a small movement, and just the partitions going through with the same conventional detailing. So you will have to step. And I think like it's like that psychological barrier of like, I was saying before, like all buildings move. If they were to tell you you're gonna be in a building that moves, your first reaction is like, wait, hold on a moment, what are we talking here? But at the same time, you're like, okay, I'm actually safer here for a seismic event than a seismic event like that arrays. It's like, if you know a floor isolation system, is what they do for data centers similar, where the ground moves, but then the floor is almost isolated with this fluid viscous damper and everything. So the ground is moving, the whole building is moving, but that floor in that room, which has very large and valuable equipment, is not moving at all. So that is the same. So sometimes in big headquarters, you have this floor isolation system in a room where you have the high valuable equipment. In this case, those floors will actually be safer, you will have to accept, okay, if you know it, because you're not going to perceive it. But if someone tells you, no, this building moves separate, differently, you will have to accept that, which potentially is a barrier. But at the same time, is that point that, okay, it's actually going to be safer and more efficient. So you actually better for you, I think.
Mhm.
Thank you.
Other questions in the room? One back here. Yep.
Following on to that question about services crossing the movement joints, have you, in your computer analyses, have you taken into account the fact that that contributes some of the stiffness, some of the spring?
No. So like they will contribute. I wouldn't expect it unless because we're thinking, we were discussing this with like, we have kind of Arup University research project in our, where we're looking into, okay, how do we actually do this into an actual system, discussing with MEP people, and then say, okay, how do we actually include that? So the main distribution could go in risers that are not, that just have an interface. For example, if we have an MP room, and that level where we transition from, because at the level that you transition from rigid to solid, to movable, you experience large interstory drifts. And that could, so you can detail the cladding to allow the differential displacement. We usually have louvers or similar. You say if you have the distribution coming from that MEP floor, have a joint, a bellow joint, to go into a riser that is within that floor, but then throughout it's just the duct going up, relatively solid, or we can have conventional elbows such as seismic joint. You're right, it will add a bit of stiffness. I don't think it will be significant from the, so potentially yes, you will have to be accounted to be 100% accurate, but as we're not tuning it, and we're actually making a very, very stiff connection, it will just be a matter of, okay, if we account for it, or interesting to account for the variability, I wouldn't expect it to be large as we're not connecting a lot, but if so, it will be just accounting for it, and yes, okay, it's very stiff. That
Okay, thanks.
it's not going to be.
Brad.
Hi, Miguel. Thanks for the talk. When you do your testing there, you do like wind testing and you do seismic testing, and I understand it's very unlikely you're going to get a rare earthquake and an extreme wind at the same time. But you do take into consideration that if you have this rare earthquake, there's likely to be a wind blowing at the same time. And how would that affect the system?
But yes, there's always going to be wind. The probability, as you mentioned, of both critical events happening at the same time is very unlikely. Hence, so what we do for tall buildings, you have the maximum considered earthquake. I was trying to remember if we apply any lateral load as in wind. No, we don't apply anything. Yes, no, we only have the gravity load. So you don't, when we check that maximum considered earthquake, you don't generally account for any wind load applied to it. You say yes, for when you do the load combinations per Eurocode, you can account for 30% wind, just with the with maximum kind of like say gravity loads, dead load and knife load. So you could account for a certain portion of it. Eurocode does not really require you to that once you have like say 30% mass, the quasi-permanent mass for gravity, and then seismic. Then going to your question, how would you actually, how would the system respond to it? In a way, the short answer will be better potentially than a conventional building, because we have more damping, we're less sensitive to dynamic excitation. We have obviously not tested it. And whether, I mean, if the building is vibrating, it's already, imagine the situation just theoretically, the building is vibrating at resonance, very high excitation, and then you get a seismic event. It's like how that's the interaction of the frequency content of the seismic event play with the frequency content of that excitation, which is first mode, essentially, in every building. If you get, say, the Great East Japan earthquake, what happened, they were like, the tall buildings were subject to long period excitation, so the tall buildings in Tokyo experienced significant damage despite the earthquake was really far away, because they got the long component. If there was a typhoon happening at the same time, they could both match, and I think you will get an amplitude in response, potentially more resonance, in which case a conventional rigid tall building would be very bad. This one, as you have damping, you can drastically reduce, you will increase. So you get a peak in demand, but potentially not as extreme. I mean, obviously not as extreme as could be a conventional rigid one, but it will be detrimental, obviously, I think, if both frequencies are together.
Other questions in the room? Yes, David.
Dave Hawthorne, Geological Survey. I was just curious, does the type of seismic wave have any, will damping cope with a P wave in the same way as it will cope with an S wave or a surface wave, indeed even the direction, or is it simply frequency and displacement that's relevant?
So the type of earthquake does make a difference. So like we tested, for example, for pure pulse earthquake, which is when you have like shock excitation, and that was detrimental because so that in all not detrimental, sorry, let me reword. We had a worse performance than compared to say if you have a far field kind of excitation where you get like large kind of harmonic line, the system starts building up, and this system starts to resonate out of phase. Then it's very beneficial because like the response starts increasing, but you're relatively low. Once you go to near fault, it proves like it's slightly worse than far field, but relatively similar. Pure pulse is a bit worse. So I think we published a bit like on the second conference in 2023, we presented 2 papers. One of them was introducing the system. The other one was looking at the response of the system to different kind of excitations and as well playing with different stiffnesses. On that one, we're checking that 7 pure pulse, 7 near field, 7 far field. And what we were getting as well was like pure pulse was a 23% reduction versus I think was far field, so near field 32 and far field 37% reduction. That talking from memory, so don't take my word for it. So it does make a difference, yes.
Thanks very much, Miguel. I was just wondering what you thought the next step would be with your idea. Is there more testing to go, or do you reckon it's kind of nearly ready?
It's nearly ready. No, so we are. So yes, like the key step that we saw for implementation is getting the wind tunnel. The wind tunnel was okay until you actually get the wind tunnels that you show that it works. There's still a question mark that anyone can ask you, and I think it will be logical. Once we have done the wind tunnel, we think that the concept is ready, and we might still. Our intention is to keep doing investigations and keep looking into more things and variations of the system, but the concept we think is there. It's more of okay, we're looking now. So we're doing kind of a small thing now. We might publish at some point. Looking okay, how do you actually implement this in a building? What is the implication? Like not just the implementation detailing, I think all the how do you physically materialize every single component, and so on beyond that idealistic representation of that simplified almost spring, which you can get springs of that. But what is the best way to actually implement it? Ideally, so the kind of thing is okay. Yes, there's if someone comes to you and says, "Oh, we have this building in Taipei, Philippines, kind of somewhere where you have high wind and high seismic, which is the ideal place where damping is extremely beneficial and you can save millions out of it." And you say, "Oh, is this?" I mean, we have tall buildings, but it's like it's not always the system is not always the right answer to every question. So as I show you, there are many types of damping systems, and depends on every building which one is the best one. Is if we find the right building, we say, okay, let's look into it a bit more in detail, applied to every case. So yes, we're planning to do more testing, we're trying to do more things because we're curious, at least I'm having great fun looking into it. But it's also okay, we think the test of concept and how it will actually be implemented is more or less shown with these studies that we've done.
Miguel, thank you very much. I was just wondering if you saw any difficulties with applying this system to slightly more complicated building geometries. So some of the lovely towers you showed are slightly different to a conventional square straight up. And I was wondering, it just seems a bit harder to make it work in my head.
Yes, so that's correct as well. So the first paper that we published, for example, we're looking at a mega frame, which is because that's the most efficient lateral system that you generally have. You can go for really high buildings, and that's when you have the cores on the outside, and you can identify a part of the floor that can move differently. What happens, for example, if you have, and that's, well, I cannot go to the very beginning, but for example, the idea came, if you see the Caja Madrid from the very beginning, the first tower that I showed had the cores on both sides and the floor in the middle. That floor can actually, in the weak direction, you have the I section, and the weak direction, you have the floor that could actually move. It does depend. Central core is the easiest one because you can just defend around. Mega frame as well, which is the one we covered in the first paper, is also, or the Caja Madrid one is also a very simple one. Other portions you might see, the third tower, the Commerzbank, it has a triangular shape with the cores in the corner. You can have this portion of the core of the floor is moving in plane. So it's on a case by case basis. There would be many configurations where it might not work. And that's what I'm not trying to say by no means that this is the new panacea that we should have it anywhere. I think there are many damping systems, and it's very good that we have so many, because each one have pros and cons. And there's some cases that some are beneficial, others are other, but it's good to have that awareness, which is also what I was trying to show, given that relatively long introduction. We have many possibilities, each one with pros and cons, and it's like I think this is something that can contribute to the conversation, add value in some locations, but maybe not in others, which is fine.
And one from Brian.
Yeah, just picking up again on the testing there, you mentioned that you didn't want to break your models, you didn't want to push them too far. And I was just wondering, you know, if you're not testing to destruction, how do you know what happens maybe for an event greater than the design, the extreme wind or the design basis earthquake that you've selected?
Yeah, so that I think is worth differentiating, which is where is the design win. And so because in this case we were testing beyond the design win, and the ULS design win I think was, I don't remember right now, but it was more than so usually like the Eurocode we test for 1.5 versus the 50-year win. American they test to 700 years design win, which is a factor which is slightly less, accounting for the hurricane. So we were testing beyond that 1.5 of the Eurocode. And yes, if you test like what is going to happen? So like if you continue, so there's a point where you get VIV and then the response continues, and so you get excitation and then the response keeps increasing linearly. It's just when engineering dynamics. But then I think it's interesting as well to differentiate between the buildings and the tower. So the physical model could collapse. And yes, it was just basically assessing the level of vibration that was exceeding and how comfortable we were at that violent vibration, and because it was very difficult to predict. But we don't think there's going to be a transition. So once you have VAV, and that's actually something that we're planning to look now, because the rigid model could not take it, but we're planning to use the damp model to assess, okay, that model exceeds less violent vibration, how does it perform under VIV? If we keep increasing to reach, so we're just slightly after this 180 kilometers per hour, around there we have it because of the building shape. But we don't think there should be, so that's one of the things that we have discussed with also people in Arup or Wind or people from the Wind Tunnel test at Imperial. And we don't think there should be a change in performance, despite we don't push it to destruction. Now we might be a bit more brave on what we do, but I don't think it should change the response.
So could take one last question in the room if there is one.
Someone at the
Ian?
very end, if they have any questions.
Oh, is there someone at the back, or otherwise I think.
Oh,
Oh, yeah, we've got one just at the very back there, sorry. Valentina.
Thanks for your presentation, Miguel. Just wondering from the sort of maintenance perspective, where you have a damper that would undergo some sort of ductile deformation in the case of an extreme seismic event, how easy it is, in your idea, to replace these dampers? Like in the case of a friction damper, you probably have to replace it after it displaces quite a lot. But then because you're supporting so much of building off these damping elements, do you think all of these dampers would have to be, I guess, replaceable, or what's your sort of solution to that?
Yeah, so I kind of have a few points there. So first, so our intention was, so we look into it at the very beginning. It's like, what if we allow some nonlinear behavior within this? So we have the fluid viscous damper that behaves essentially elastic, so there's just movement between them with no damage, and we have the spring in parallel. We investigated because it can perform better if the spring experiences some nonlinearity, so like as the building sways, and that damper mass is allowed to go a bit farther, and that can like actually gets more in tune, so it gets farther away. But as that was only applicable so we only tested for seismic. As the seismic excitation fluctuated back, we didn't see such a big improvement on response. Tiny bit, but we didn't thought it was worth it. So we keep everything linear. The dampers themselves, so the fluid viscous damper, tailored devices of equipment Australia might tell us, we're maintenance free, only repair every 5 years, only visual inspection every 5 years, and they have a 50-year guarantee, or that's what they usually say in the catalog. And you do need to inspect them, but the good thing is we have a redundant damping system with many dampers per floor. If there's one that you need to replace, you can just take it off. It's not going to affect the response. And as well, so you can have metal seals, metal seals like the one that, I don't recall what is the name right now, that are maintenance free, the one that they use in aerospace. I don't think there's a need to go for that, because any kind of buildings in Millennium Bridge, which is very tricky to access, you just have fluid viscous damper, and just maintenance, nothing has happened there for a long time. But as well as it is true what you say in some cases, well, in this case, the dampers are providing lateral stability. So in reality, is that all gravity loads are transferred straight down, undamped, so it doesn't really affect that you're supporting a large portion. You are providing lateral stability, yes, but you can always replace it even by a rigid interface. Okay, remove this, put a rigid case, there's one floor, it's not going to change anything. For a friction device, or say backing restraint braces, yes, that is the case, which is that's kind of the usual difficult conversation you have with your client. You have these massive braces, which are amazing to put at the early stage of the project when you have the tower crane, you have everything. But after a large event, how do you approach that or replace a backing restraint brace that has experience of the permanent damage? You don't tend to have to replace them after every single event. So backing restraint braces, I'm talking about them because I know them more. They do have some damage accumulation scale, which is depending on the seismic events. They can undergo several seismic events, and depending on the damage they have, usually like core brace or Nippon Steel will come to your site and assess what is the level of damage and tell you, yes, you can still have it. Or if the whole core is yielded and plastified, they might tell you, okay, no, sorry, you have very long elongation, or if your linearity has pushed the building too much, you might be, okay, yes, I need to replace that. On that end, for example, the friction dampers, the Tectonus one that is self-centering, is beneficial because it can come back to the original position. But most of these dampers, or sometimes they can withstand several earthquakes. So fluid viscous damper, they don't yield, but they could have leaks, for example, if there's a really violent event. But that's part of the natural processing rather than demolishing the whole building, because you have all the coupling means completely destroyed and yielding in the core walls. It's just that one element that you take, put it away, and bring a new one, which is one of the big things of like having that kind of all the damage concentrated on those elements, if anything.
Cool. I think it'll be good to draw a line under that. But thank you once again, Miguel. Just before we give the last applause, fancy a drink over at the Westminster Arms?
Yeah,
So we'll,
sure.
if everyone or anyone who wants to come for a quick drink over at the Westminster Arms, just around the corner. That's the right name, right, Ian? Yeah. Yeah, so please do. And otherwise, let's give Miguel a round of applause.